I bought one of those inexpensive buck-boost converters online, and this thing can take anywhere from 5 volts to 30 volts and convert that to 0.5 to 30 volts. So I figure if I combine that with old laptop power supply, I can make myself a cheap little benchtop power supply. Buck-boost converter schematic is typically drawn like this, where this is the switching transistor switching at high speed, and this is the inductor, and that charges the inductor with a positive current, and when this disconnects, the inductor wants to maintain the same current, so it reverses polarity and pulls in electricity this way, which means the output is negative. So I prefer to draw it like this, where up is positive and low is negative. So the thing with a buck-boost converter is its output is always the reverse polarity of what's going in. Now, as expected, the ground goes straight through, but what's interesting is the input is positive and so is the output. So how does that work? But looking at this thing here, the main inductor on here has actually got two windings, a yellow one and a red one. And so this inductor is actually more of a transformer, a flyback transformer to be specific. And so when it discharges, it doesn't discharge through the main winding, but through the extra winding, which has got the same number of turns, but basically we switch to polarity on it so that we actually get a positive output instead of a negative output. So I had the idea, why not just add another winding to that inductor so I can have a second output which is isolated from the first one. And that's what I did with this one here. I also took it out of its case. Got the same number of turns on there with just telephone wire, so let's try that out. So I'm monitoring my extra winding with the scope, and on this thing I can adjust the voltage up and down, and the bulb gets dimmer and brighter with that. The yellow is the waveform of my extra winding I've added, and negative is the charge part of the cycle, and then positive is the discharge part. And the charging is negative on here because my winding is the reverse polarity of the primary winding. Now if I adjust the output voltage, we can see the discharge voltage goes up, and so does the output voltage, which I've got in blue, and the period of the charging increases as I increase the voltage, decreases as I reduce it. And if I add a little bit of extra load, then the charging period also increases because we need to put more on the output. And this ringing here is after it's done discharging. There's a bit of an idle period where there's nothing hooked up, so that's just the self-resonance of the inductor. Now I have my new winding going through a diode, charging up this capacitor and the load on there. Basically same thing as what we would have in the first place, the diode and a capacitor to the load. And now when I adjust the voltage, both lights go up, and of course my output voltage goes up. The blue is now my new output voltage. And this is not independently regulated, which means if I put extra load on the main output, the voltage rises just a little bit, and if I add extra load to this output, the voltage does drop a little bit, although the duty cycle for charging does increase, this duty cycle here, as I add extra load, because the second winding is essentially stealing some of the discharge cycle, so it knows it needs to charge more. But where I run into problems is if the original load is disconnected, then it doesn't take very much to charge the non-loaded capacitor on this one, which is why our voltage really drops. So we do need at least some load on the primary. I wanted to see how clean the output is, which is the blue channel, so I just changed that to AC coupled and cranked it up so it's 500 millivolts per division, so 10 times bigger. So we can really see output ripple. So we've got like a big ripple here, but also some spikes, especially this one here. And that goes up by, 4 divisions, so 2 volts, so that's a bit much. So I'll try to filter that one out first. So I just added a homemade inductor and a film capacitor. Essentially, after the diode, I have the film capacitor here, and those are really good at high frequencies. The homemade inductor at 8 microhenries, and then the cap I had before. And now, if I look at this, the spike here is greatly reduced, but if I zoom in on that spike a little bit, and unfortunately the triggering is a bit inconsistent, so I'll just do a single shot, and that there is about 100 megahertz. I've got the cursors on it, says 89 megahertz. And basically I've got far too much parasitic inductance on all my clip leads and such, which is probably why I'm not able to suppress that very much. So if I build that up a little tighter, that'll probably go away. And I thought I'd compare how clean that is to the actual output of this thing. So I've got my green tag probe on here. So this is the spike from my output, and switching the probes, it's actually worse than the output that I've made, so their filtering isn't optimal either. And zooming in on this, we've got a similar sort of 100 megahertz ringing on there. So I've just added an inductor and a capacitor on the main output of this thing, and that doesn't seem to reduce the size of the spike here at all. So I decided to probe it with a separate scope. So this one actually runs off of battery, and right now it's set at 20 millivolts per division, so zoomed way in and I see the spike. So if I set it to 500 millivolts per division, I see nothing. So that tells me this is a grounding issue here, in that this whole output is bouncing around, and at those sort of frequencies this is a big problem. So having a battery powered scope is very handy for this sort of thing. So if I just disconnect the ground lead on this thing here and watch that trace, notice how much bigger that spike gets. It's just huge. So basically just ground bouncing around, and that is a problem with switching converters and high frequency noise and stuff like that. Makes me appreciate my homemade power supply, which has no regulator, no switching converter, so there's no high frequency component at all in that one. Or this one here only goes to 250 milliamps, but it's a linear regulator, so also no switcher. I put the filter and rectifier on this separate piece of perf board, and I also made extension cables to go between the control panel and the power electronics so that I have more space around it so that it can cool from both sides. The fancier ones of these that handle more current have a cooling fan on them, but I want to avoid that because those make noise. So now I'm going to build a housing for this thing, and I was thinking of just using the regular front panel for this thing, but then I made a little mistake because while experimenting I had this out, and then I powered it up with this thing plugged in backwards, which of course it didn't come up, so I put it back in forward, and it was basically like this. It wasn't putting out any power no matter what I twisted on here. Meter still worked, so I figured I might as well take this thing apart. So I extracted the front panel out of this, which involved busting this thing. So that's no longer an option. But then I realized I hadn't busted it at all. I just forgot to push this button here, which you need to do to get it going. So it wasn't busted after all. So now I have to make a new front panel for this, and one out of wood, and I've already milled one out just to make sure it actually fits. And I started out by photographing this thing and importing that into SketchUp at 1:1, and then drawing the shapes of all the little bits that stick out on here roughly just to make sure I have clearance. And then I flipped that model upside down, and this is looking at the bottom of it, and exported that as a collada file, and then running that through a complicated Python script that I wrote with the help of AI. And here's my toolpaths that I can sort of zoom through, and it also shows the mesh that I'm milling too. And here's my third or fourth try at this, and that fits in here nicely. The LEDs kind of are recessed, and the buttons still stick out far enough I can push them. And I've got this loaded up for milling on my Carvera Air. Oh good, I didn't screw it up. Let's see how that fits. Good. And here it is mounted in a sort of a case. The challenge was this power electronics PCB, the one in the back, doesn't have any mounting holes. In fact, in here it's just held by these pins in here, so I had to shape these blocks to fit around some of the electronic components. For my own perf board, which has got much less on it, it was much easier. Now I just need some kind of protective housing to go around it. And I figure this microwave oven door screen will be just perfect for that. Now I still need to cut a hole right here, and I can't just drill that because that would just tear it apart with all those holes in it. So I'm just going to try and shear that. And now I've got both outputs in series to charge the capacitors up to 60 volts. That was better. And does it make sense to go through all this effort to build a little gadget like that? Not really, although what would make sense is to just take one of these and put it in a little box, because I think these are kind of handy and they're kind of cheap. As for that 90 megahertz ringing, I've realized it's well outside the bandwidth of any circuit I'm going to work with, so I'm just going to ignore it. But looking at this thing in spectrum analyzer mode, we do have a peak around 90 megahertz, and another one somewhere around 35 megahertz, so I don't think these modules would ever pass FCC certification. I don't think I've made this one that much worse. And I can even look at that in time domain on here. So we have the high frequency ringing right here, and then at another point in the period we have lower frequency ringing. And I suspect that's the inductor ringing with one or two diodes disconnecting, because the diodes have capacitance which would lower the resonant frequency of the inductor. And zooming out, this repeats where I've got the cursors at about 100 kilohertz, and that corresponds to the switching frequency of this gadget in here. And it's not even hooked up, I've just got the wire kind of hanging out there. It's just picking it up over the air. So it turns out I have made it worse, because taking one of these unmodified ones, and I turn it on and I try to look at it with the spectrum analyzer thing, I don't pick up a whole lot of noise from there with the wire right next to it. Whereas with this one here, I pick up quite a lot of noise. This is on, off, on. But it turns out if I connect my two outputs in series, which I intend to do most of the time anyways, that suppresses the noise a fair bit. This is connected, disconnected, connected, disconnected. But if I probe around the unmodified one and I put the wire right next to the inductor, I pick up quite a lot of noise, including that 90 megahertz thing. The 35 megahertz seems to be an artifact of my modifications. So the problem is my extra winding on the inductor is completely isolated from the other circuitry, so nothing to ground the noise away. And I bring it out to this board, which is also isolated, and that takes it out to the front. So inadvertently, I've taken the noise from the inductor and broadcast it. I just added this ferrite choke here to suppress common mode noise from this winding here. And checking it with this spectrum analyzer thingy, that greatly suppresses the noise. I still get the 35 megahertz spike here, but if I connect the two outputs together in series, that suppresses it a fair bit. I also added a 10 nanofarad capacitor to tie the two outputs together, figuring that should suppress the noise a bit. But it's not as effective as jumpering the outputs in series, which I'll be having that most of the time anyway, so by default I'll just have this jumper on so it doesn't mess up the 35 megahertz band so much. And in terms of these cheap buck-boost converters, it turns out neither of my other two actually worked. One of them didn't come up, and that turned out to be a faulty display. Just look at the solder joints on here. It looks like they tore off the pads when they inserted the other circuit board in there. So the display on this one doesn't work, and on the other one, the power electronics didn't work. It didn't produce any outputs. So swapping the two, I got one that works now and two defective boards. You don't expect perfection from AliExpress. As for this FNERSY scope, I reviewed that a few months ago and I pointed out a lot of shortcomings to it. But it's actually so handy to use because it runs off of batteries, so I can just hold it up to something. It doesn't have power supply noise issues that, for instance, this scope does have because it runs off a USB adapter. And it's so quick to use, so for instance, if I wanted to go into spectrum analyzer mode, there I'm in spectrum analyzer mode. So real handy. It's also got a annoyingly loud fan on it, but to some extent that's useful because it reminds me to turn it off when I'm done using it, because the battery on it only lasts about 2 hours.